Introduction to Databases. Hello and welcome to DSN, your destination for academic insights on data systems. In this first tutorial, we lay the groundwork by defining what a database is and why it's important. A database is commonly defined as an organized collection of data, generally stored and accessed electronically via computer systems. 1. In simple terms, it's a structured set of information, like student records or sales data, that can be easily managed and queried. Early data management often relied on file systems, but these had limitations such as redundancy and inconsistency in data. Databases, especially when managed by a database management system, DBMS, provide a centralized and efficient way to store and retrieve data. This ensures multiple applications and users can access consistent information without conflicts. The core role of a database is to serve as a central repository of information, supporting operations like searching, updating, and reporting in a reliable manner. Brief history of databases. To appreciate modern databases, let's briefly travel through their history. In the 1960s, the first DBMS were created to handle business data. Notably, Charles Bachman's Integrated Data Store, IDS, and IBM's Information Management System, IMS, were early systems using hierarchical data models, too. These organized data in tree-like structures with records and subrecords. By the late 1960s, network models, allowing more complex many-to-many linkages, also emerged, too. A major revolution came in the 1970s when Edgar F. Codd introduced the relational model, which organized data into tables, rows and columns, and formed the basis of relational databases. 3. This model, alongside the development of SQL, structured query language, for data manipulation, led to relational systems like Oracle and MySQL in the subsequent decades. 3. By the 1980s and 1990s, relational DBMS dominated due to their flexibility and ease of use, replacing older hierarchical, network systems. Modern era. Today, while relational databases remain prevalent, we also see NoSQL databases, e.g. document stores, key-value stores, graph databases, rising to handle unstructured or big data needs. 3. This historical evolution shows how databases have continually adapted to store growing volumes and varieties of data. Role of the database. What purpose does a database serve in an information system? In essence, a database, together with a DBMS, acts as a central hub for data and applications. Instead of data scattered across files, a database brings data into one system where it can be consistently managed, queried, and shared among users and programs. 4. This centralization addresses many problems of the old file-based approaches. For example, a DBMS minimizes redundancy, avoiding duplicate copies of the same data, and prevents inconsistency, so all users see the same updated data. 4. It also enforces data integrity rules, meaning the data meets certain quality constraints at all times. Another key role is handling concurrent access. In a multi-user environment, the DBMS ensures that two people updating the same record do not corrupt the data. Security is also crucial. Databases allow defining permissions so that only authorized users can view or edit sensitive information. In summary, the database's role is to be the reliable backbone of software applications, from websites to enterprise systems, ensuring data is stored safely, retrieved efficiently, and maintained accurately across all uses. 4. Think of it as the library or archive for an organization's information. Introduction to DBMS. Now that we know what a database is, let's introduce the Database Management System, DBMS, the software that makes databases useful. A DBMS is essentially an intermediary between users, or applications, and the data itself. Formally, a DBMS is software designed to handle, store, retrieve, and manage data in databases, providing an interface for users and programs to interact with the data. 5. Instead of applications reading raw files, they send queries, requests to the DBMS, which then performs the operations on the underlying database. Key functions of a DBMS include allowing users to create databases and define schemas, the structure of data, like tables and fields, enabling querying and updating of data through languages like SQL, and ensuring integrity constraints are not violated. For example, you can set a rule that no two customers have the same ID. The DBMS also manages transactions, grouping multiple operations into a single unit of work that either fully succeeds or fully fails, which is vital for consistency. This is the A in ACID properties: atomicity, consistency, isolation, durability. Additionally, a DBMS handles performance optimization, using techniques like indexing, which we'll discuss later, to speed up data access, and it schedules disk access and memory usage to efficiently answer queries. In simpler terms, if the database is a large repository of data, the DBMS is the smart librarian that knows how the data is organized, how to find things quickly, and how to keep everything in order. Popular DBMS examples include MySQL, PostgreSQL, Oracle, and Microsoft SQL Server for relational databases, as well as MongoDB or Cassandra for NoSQL systems. By using a DBMS, developers and users can work with data at a high level, through queries and commands. Without needing to worry about the low-level file operations, the DBMS takes care of those details behind the scenes. Attributes in DBMS. Before closing this foundational session, let's touch on a basic piece of database terminology: attributes. In database design, particularly in the relational model or in an entity relationship model, an attribute refers to a property or characteristic of an entity. More concretely, in a table, relation, an attribute is a column. In an diagram, it's a property of an entity set. Attributes are the data points that describe an entity. For example, if we have an entity, student, its attributes might be name, student ID, date of birth, etc. Formally, attributes are pieces of data that give more information about an entity, used to describe and distinguish one entity from another. 6. Each attribute has a value for a given record, or a value of null if unknown, missing. Collectively, the set of attribute values for an entity instance, like a particular student's name, ID, DOB, etc., comprises a tuple or row in the database table. Attributes are crucial because they define the structure of the data that the database will store. When designing a database, one of the first steps is deciding what attributes each entity should have. Attributes can have types, e.g. integer, text, date, and sometimes constraints, like an attribute, age, might have a rule that it must be a positive number. In an model, attributes are often drawn as ovals connected to their entity rectangle, indicating things like primary key attributes, underlined, or multivalued attributes, double oval, etc. To illustrate, consider a student table with columns. Student ID, name, major, GPA. Here student ID, name, major, GPA are attributes of the student entity. Attributes thus help organize data into meaningful fields. Without attributes, an entity would be amorphous and not very useful. With attributes, we can ask specific questions, e.g. find the student name and major for all students with GPA above 3.5. Attributes make the database structured by breaking data into its logical components. Transition. With these basics covered, the definition of databases, a historical perspective, their purpose, the concept of a DBMS, and attributes, you now have a solid foundation. Up next, we'll build on this by exploring how data is modeled and the fundamentals of SQL. Stay tuned, and if you found this introduction helpful, please subscribe to DSN and give this video a thumbs up. Your support helps us continue providing in-depth lessons. Don't forget to turn on notifications so you won't miss Script 2, where we dive into data models and query languages.